All right, hello and welcome to week 5. Today we will be discussing projectile motion. This is one of our more hands-on fun labs to do when we're actually in the lab room. I'll give you a demonstration of what it would look like, but first we're going to talk a little bit about the theory behind this lab. So what we're looking at here is we're analyzing the motion that a ball would make after being shot out of a gun. So we have our Y and our X axes that would be at the place of the starting firing of this ball. We know in our X direction, then the ball is going to be subject to V naught times T plus 1/2 acceleration times time squared. Our Y direction, same equations. However, in our X direction, we know there will be no acceleration once the ball is shot. It's just going to continue moving in that direction without any sort of force of acceleration acting on it after the initial shot. So our acceleration times time can then go to 0, leaving us in our X direction with simply V naught times T. If we solve that for T, we have X over V naught. This is what we're hoping to find here, this initial muzzle velocity of the gun. In our Y direction, it's a little bit more complicated. Once the ball is shot out, we can eliminate this first instead of second, and the accelerated force we have here now will be gravity acting on our ball in a negative direction. But again, if we look at our axes as the starting point of the gun, and we look at this Y direction down where the ball will be falling, that is our negative Y. So both of our negatives cancel out. We are left with just Y equals 1/2 GT squared. Using this equation right here, we can substitute in for time. So we have X over V naught squared. And now we can solve for this variable that we are looking for. Again, we are trying to find the velocity that the ball is being shot out of the launcher. Okay? We are going to be taking 2 measurements. That's it. We are looking at the height, our Y of the ball, and our X, how far the ball will actually shoot. So if we were in the lab, this is the device that we would be using. We have a launcher right here. If we get a little bit closer here, we can see there is a mark on the launch which shows us exactly where the ball will be shot from. We would push the ball in to hear 2 clicks. We would be measuring with a plumb bob directly from this launch position. Again, this X directly on the center of the ball to the floor to see exactly where the ball would be starting from. This would give us the start of our distance. And then we would measure from the floor to the bottom of the ball to get us our height. So we're looking for this starting position of the ball as our zeros of our X and our Y, seeing how high it's going and how far. So we would simply lift this trigger, the ball would fire, we would have a sheet of paper taped to the ground, and it would show us exactly how far, where the strike point was, and we could measure accordingly. So in terms of measurements, this lab is fairly straightforward. Again, we are just looking at our 2 unknown variables right here. Our X, how far the ball is actually going to travel, and Y, which is simply our starting height, how far the ball starts above the ground that it is going to strike. So we have performed this experiment for you multiple times with multiple variations. You are going to use the photographs available to you to deduct both the height based on, again, a perpendicular measuring stick that will show you exactly the floor to the bottom of the ball. Again, so we're looking at the bottom of the ball, because if we are looking at how far the ball travels, again, we're starting resting within our launch gun, and then it is striking the ground. So for our Y, we are measuring our height from the bottom of the ball in this gun to the floor. For our X, we are looking at the center of the ball. So on our launching gun, it will be a lot clearer for you in the photographs that were already taken, that'll be provided for you to extrapolate data from. There is a small circle like this in the center of the ball's position. So it marks directly what this center point would look like. So we're going to measure down to the floor, again using our plumb bob. Let gravity do its work. It will simply hang down, provide a shadow that would give us the direct exact position that we would measure our starting distance from. And then there will be dots marked and circled on the strike pad. So we would have a piece of paper right here with a target, and then we'd have different strike points. Okay? So the goal is to have a spacing where you have 2 or 3 strikes within a similar range of one another so that we have consistent data. We've labeled them 0.1, 0.2, 0.3, 0.4. And you are going to figure out exactly how far the ball traveled to each of these locations. So that will be our X's. Our ball is not always going to travel in a directly straight line. However, we know from the location of the plumb bob exactly where we're starting. So if our ball travels slightly up, slightly down, we know this will always be a right triangle. So if we're looking for an exact distance that the ball traveled, again, if it's not going directly from point A to point B, but our rulers are, you can use Pythagorean theorem. We have A squared plus B squared equals C squared. So if we are looking for this line, this would be our C. Doesn't matter whether you assign this as your A, your B. We can find the distance directly traveled along the ruler stick. And again, there will be a ruler here perpendicular. You can find the height that it traveled above this straight line for your B. Okay, so if you're looking for this exact distance that the ball traveled, you have to account that there will be variations vertically as well as horizontally. So again, we need that straight line, simply looking at a right triangle. So again, every single right triangle will have Pythagorean theorem. So you can use the horizontal length and the vertical length to see exactly how far this ball traveled from point 1 to point 2. Okay, any questions on that, feel free to email me, but it's really as simple as that. So if you're looking for this C, C would just be the square root of A squared plus B squared. Okay, and the A and B, they're simply the lengths that you're getting directly from the photograph based on the measurements of how far this ball traveled. Okay? So once you have your X measurement and your Y measurement, again, Y is simply just the height from the floor to the bottom of the ball, we can solve for our initial muzzle velocity, okay, this V naught. Gravity, as we've seen before, is a constant. So it will always be 9.81 meters per second squared. And then you're just plugging in the distance, your X squared, how far the ball traveled, and you're dividing by 2 times Y, our height of the ball off of the floor. Okay, so this is how we're going to find our initial velocity of the launcher. Using this value right here, our initial velocity, we can then try to determine how far the ball will shoot from any height. Okay, so going from a known initial velocity, so we are going to assume that if we put the ball into the gun, we click twice, it will shoot out at the same speed every time. We are assuming a consistent initial velocity. So now what we're doing is we are varying how high off the ground we are starting from. If we were in the lab, in person, performing this experiment, I would give each of you a target labeled as such. So simply looking like a bullseye, you would measure your brand new height, again, just the distance from the ground to the new height of the gun, and then you would solve for how far you think the gun will now shoot with a new height. I will put up a little experiment online that you can play around with. You can see how changing, in this we're shooting out completely horizontally. You can change the muzzle angle, you can change the height, you can change all of these things and see how it will impact the path that the ball takes. You can play around with that. Obviously, if we're starting higher, we do expect the ball to go a different distance, playing around with that. This way, when we have a new y, again, we're just solving for a different variable. So this becomes our new equation. Our x equals the square root of 2y times v naught squared. So again, you're using your v naught that you found right here, and you're just plugging in for y this time instead of x. So we're trying to find how far this ball will now shoot from a different starting height, okay? So again, if we were in the lab, we would be graded on how accurately you calculate this, and we would look at exactly where your ball would strike on this target, and that would be what would determine your score. Obviously, we cannot be doing that right now when we're in a remote format. So you will be just performing the calculation and then performing an error propagation. So we're gonna have our least count, our absolute error. Similarly to our last few labs, again, we're just using rulers. However, we're using actual rulers, so be careful in terms of the sensitivity. The least count, the smallest divide on the meter sticks that you're looking at when you're extrapolating your data. So we'll just have, obviously our ruler and our meter stick are going to have the same least count, the same sensitivity. So then we're gonna take those absolute errors and we're gonna perform an error propagation. We did this in week 1. You can reference your error sheets or your lab handouts if you saved it from lab 1, week 1. We're going to try to find how much error we think was found when we calculated our V naught, okay? So using the formula we found from before, anytime you have multiplication or division, you're looking at simply adding together these errors, okay? So we saw in week 1, you're taking your delta V naught over V naught. So delta V naught is what we are hoping to solve for. Because in our equation, our x squared has an exponent of 2, we have 2 times delta x over x plus delta y over y. And then because our entire equation is taken of the square root, that is where this 1/2 comes from, okay? So exponents come down in numerical terms, okay? So if we just solve for this delta V naught, we have V naught, again, this is the number that you found in part 1 of the lab, times delta x over x, where delta x is your absolute error associated with your measurement of this distance, plus 1/2 delta y over y. Again, delta y, the absolute error associated with your height measurements. because we are using meter sticks and rulers for both measurements, your delta x should be equal to your delta y in this lab, okay? And they both should just be your absolute error, okay? So we've seen these numbers before. Do not overcomplicate this. We're just looking, we've seen in the past, our rulers are double-sided. They do tend to account for higher errors than some of our more finely tuned or digital measuring devices. So we're just seeing how much they contribute because of their inherent sensitivities to our actual value of V naught, okay? So for our error analysis, that is it for this week. You would have least count, absolute error. Again, we just have the single device, or obviously if you would like to, you could say ruler and measuring stick. However, they will have the same least count and absolute error. And then you're doing one error propagation formula looking at your initial velocity, okay? So this lab should be fairly straightforward. Again, in the lab, it is a lot of fun, very hands-on, getting to shoot the ball out of the projectile launchers, getting it to a point where we see a very good grouping of strike points, calculating out our initial velocity, again, using this equation right here, which is printed out for you directly on the handout, as well as these transitions of formula manipulation going from point A to point B. Make sure, again, you're careful with your parentheses, careful with your square roots, making sure the entire body underneath the square root is typed in prior to hitting the square root button. Taking the initial velocity we found in part A, you are then going to use that with an unknown new height, assuming that our velocity will again be consistent because we are shooting it out of the same setting of the gun, and use this to find our new strike point, how far we think the gun will now shoot based on our new starting height. Okay, so make sure you have all of the necessary sections in your lab report, your objective in your own words, your theory defining your variables, apparatus, procedure, your data, your calculations that will come directly from here, and a well thought out conclusion. Okay, no graphs this week, no LSQ, simply just our least count and our error propagation. If you have any questions, feel free to reach out, and good luck crunching your data.